Good morning, my name is Trevor David Rowan, and today I will talk about machine learning approaches for magnetic characterization. And I'll be focusing mostly on two-dimensional magnetic materials for this presentation. Let's start first with an outline. I'll begin with talking about motivation for this talk, and I'll be focusing on the challenges for materials discovery with a focus on the discovery of two-dimensional magnetic materials. We'll spend most of the discussion talking about machine learning, introducing you to the important concepts of machine learning. And then towards the end of the talk, we'll connect that with the search for new two-dimensional magnetic materials, their thermodynamic and magnetic properties. Machine learning is an extremely interdisciplinary field of study. It is a subset of AI, artificial intelligence, and intersects with data science. Data science itself is a combination of statistics, data visualization, study of databases, and data mining. Now, recently, the interest in machine learning has grown exponentially since perhaps around 2012, 2010 or so. There's been an increase in machine learning or data science in targeted advertisements from companies such as Facebook. We can use machine learning for movie recommendations when you watch Netflix, for instance. And very recently, it's become important for self-driving cars, AI in particular, email spam filtering for some time now, and facial recognition. For a while, machine learning ideas or data science ideas have been used in fields such as astronomy and biophysics, but more recently, in the past few years or so, it's grown in popularity in fields like materials physics, quantum physics, and mathematical physics for solving differential equations, for instance. Now, first, a motivation. How does machine learning, or how might machine learning be useful for the study of two-dimensional magnetic materials? Consider the following. These materials, chromium, germanium telluride, shown over here on the right, or left, and chromium triiodide, shown over here on the right, were discovered in 2017, many years after the discovery of graphene. And these materials are interesting because they are the first materials that are two-dimensional, layered, showing intrinsic ferromagnetism. Now, it took many years for the discovery of these intrinsic 2D magnets to occur after the discovery of the first 2D magnet. And why is that? Why didn't discovery happen much faster? Well, in 2015, I was doing experiments on chromium germanium telluride, trying my best to measure one layer of this material for the first time. My experiment had two issues. In particular, my ferromagnetic resonance measurements had two issues. The first was that the resonance of the chromium germanium telluride was a little bit outside the range of my equipment. And also, chromium germanium telluride was a little bit chemically unstable. Now, at the time, I knew that Pablo Herrero at MIT was working on chromium triiodide, and we discussed a bit the chemical stability of chromium triiodide, and it turned out that it was worse than that of chromium germanium telluride. So I was a bit stuck. I needed a new 2D material that was potentially intrinsically ferromagnetic with better chemical stability than chromium triiodide or chromium germanium telluride, and magnetic properties different from that of chromium germanium telluride. I searched the literature. There weren't any obvious candidates, and the potential number of materials that exist in databases like ICSD or in scientific literature were really huge, and it was difficult to figure out where to look for the potential or promising candidates. So this is where my journey in machine learning and magnetic materials began, searching for new 2D materials with just the right magnetic properties using a combination of first principles quantum simulations like the ones discussed for most of the workshop, and also machine learning. But as I said, there are challenges that are involved with materials discovery, searching for new materials with desirable properties. Consider the fact that the material search space is huge. Take, for instance, the Inorganic Crystal Structure database has over 200,000 inorganic compounds. Now imagine searching through 200 compounds, doing serial experiments to try to get a good material with the property that you're interested in, or investigating all the compounds, inorganic and organic entries in the chemical abstract service that contain over 49,000 different materials, and also recognizing that a theoretical estimate for the total number of candidates of materials, including molecules small and large and crystal structures, is on the order of 10 to the 100, really a huge number. It turns out that this number is bigger than the number of particles in the observable universe. Doing first principles calculations to estimate the properties of all these materials, and even worse, doing serial experiments to estimate these properties is impossible for this entire search space. So one needs to have a different approach to accelerate the search for new materials given this very large number of materials candidates. To give this another context, I'll borrow this slide from our friends at IBM Research. And the point of this is that advances in materials drive technological innovation. This particular view graph describes magnetic random access memory and the technological innovations that occurred through advances in materials over the years. Starting in 1974 with the invention of the magnetic tunnel junction, which would happen only at cryogenic temperatures. It took almost 20 years until technology or materials were developed to have the magnetic tunnel junction operate at room temperature. And then later on, the resistance of the magnetic tunnel junction was increased by finding yet a new material which increased its performance, and years later one managed to get the spins rotating out of plane, have the easy access of magnetization out of plane as opposed to in plane, which again enhanced the performance of the material. And overall, this took a great deal, many years, over 30 years, to go from the material which demonstrated the concepts of the MRAM to one that was having industrial applications. One would very much like, instead of having this process to be over 30 years, to be 30 months or 30 days, or shorter than that, identifying the property of interest and having some mechanism or some framework to find exactly the material that will suit those properties for that desired application. The proposed framework for doing this is machine learning. Imagine taking graphene's crystal structure, or that of MOS2, or chromium germanium telluride, chromium triiodide, or boron nitride, and being able to tell its properties, for instance, the fact that graphene is conducting, BN is insulating, or chromium germanium telluride is magnetic, without doing first principles calculations or experiments. This is extremely challenging prospect, and it's akin, all these materials and searching through all these materials is akin to navigating space instead of, or outer space. We're navigating a chemical space of materials candidates, where our task is to explore this space to find just the right material, akin to finding perhaps a habitable exoplanet in astrophysics research. Now let's discuss the machine learning framework to see how it might be applied to materials discovery. In machine learning, you need three key elements: data, descriptors, or mathematical representations of your data, and statistical models. Data for materials research are becoming more accessible. Materials databases are becoming more accessible, and there are many different kinds of data that exist these days, and the kinds and the quantity are both growing. Materials descriptors are also extremely important, and there are very many talented researchers developing their careers to creating new, more and more reliable materials descriptors. Some of the simpler ones that came out not so recently are the Coulomb kernel and the bag of bonds representation. Also, data science tools exist which one can easily import to one's laptop, such as scikit-learn and Google's TensorFlow. First, let's talk about data in some more detail. Now, some of the databases that are popular these days is the Materials Project, which is perhaps the most popular, coming from the Materials Genome Initiative. There's also AFlow. These are both density functional theory, or DFT databases. There's MatNavi, which is a database developed by the National Institute for Materials Science, based in Tsukuba, Japan. There's CGDB, which is a database devoted solely towards two-dimensional materials. In addition, there's OQMD, Open Quantum Materials Database, and Nomad, and Inorganic Crystal Structure Database that I mentioned before. And these are only a few of the databases that are out there, and I imagine the number are growing almost every day. Next, let's talk about descriptors. Now, descriptors are mathematical representations of the data. An example of a descriptor is the atomic properties of constituent elements of a compound, that is, a molecule or a crystal structure, or perhaps a mathematical representation of a crystal structure created using some scheme. We can talk about examples of this for materials research in a few slides. Needless to say, the descriptors are extremely important and are an active area of research. Next are the statistical models, which are also extremely important. There are some that are quite familiar to you, such as linear regression, where the machine learning involves learning m, the slope, and c, the y-intercept. There are other models, such as ones based on decision trees, like random forests. The decision tree, an example of a decision tree is shown here. This is a silly example, the aim of which is to predict whether or not to give somebody a credit card. And let's go through it, since these decision trees may be a little bit less familiar to you. So there are three descriptors here. There's age, student status, and credit card rating. And once we traverse the tree, we'll say what is the person's age. If the person is young, we'll ask if they're a student. If they're not a student, you don't give them a credit card. But if they are a student, you predict that you should give them a credit card. And you can also, instead of just doing decision trees for classification, you can develop a scheme for doing regression. We'll talk about that a little bit later down the line. The great thing about data science, especially for material scientists, is that the data science tools, machine learning tools, exist in a so-called data science ecosystem that are very easily accessible. So one can use MongoDB or MySQL to store data, then transform those data using Python, and then to create machine learning models very easily using scikit-learn, and you'll do this later today. And then once you have your very nice results, you can visualize them using matplotlib. Now, what is machine learning exactly, and how does it work to create predictions? Now, machine learning is essentially approximating some function, f of x, which takes typically some inputs that are easily attainable, such as the properties of elements that you could find in the periodic table, and it attempts to predict something that's usually difficult to measure or difficult to calculate. That could be the formation energy or the magnetic moment of a 2D material, for instance. And this function f of x has potentially a high-dimensional descriptor space, and typically these functions are quickly evaluated. For instance, mx plus c given an x, and m and c is very quickly evaluated, giving you some estimate for some property y. Now, there's always some uncertainty uncertainty associated with a given measurement or a given calculation from the true value, and this is something one has to take into account when constructing these models. And we'll talk a little bit about this later on. So our goal is to learn some relationship, or to quantify and predict some value given some relationships. Now, the function takes as its inputs x1 through xn, where n can be a very large number, greater than 4, 3. And this is important because our human brains are good at interpreting few-dimensional space, or descriptor space, or spatial dimensions, such as 0, 1, 2. We can perceive patterns in 0, 1, 2-dimensional spaces very easily. Also, 3-dimensional spaces. If you consider 3-dimensional spatial dimensions and 1 time dimension, a 4th-dimensional space is easily perceived, but once you start with 4 spatial dimensions, this becomes quite challenging, and this isn't necessarily only applicable to spatial dimensions. You can also include the idea of concept of more than 4 descriptors as different dimensions in your descriptor space, and this becomes quite challenging for human brains to perceive patterns in this high-dimensional space. One of the great advantages of AI or machine learning is that a machine learning model doesn't have this limitation. There are 2 reasons why we want to estimate f, some function f, via machine learning model. And let's focus on this a little bit more, though I've mentioned it very briefly just a while ago. The first is making predictions. Now we want to, given some x values that are readily available, predict y, which is often difficult to obtain. And often we don't really care what the functional form of f is, as long as it does the job. It makes these accurate predictions. And we want to check if it's accurate or not by comparing the prediction to the actual value and using a loss function to do that. Typically, the goal of these machine learning models is to minimize the loss using this scheme. And notice that there's always some term that can be reduced, which is arising from the error in the data. Another important goal of machine learning that's actually growing more and more in importance is inference or interpretability. You want to learn how the inputs are affecting the output, how x values are relating to the target property y. In this case, the goal isn't just to make a prediction, it is to understand the relationship between x and y. This lends itself to interpretability, which is very important if you want to understand something, some physical mechanisms of a material system given a particular property, for instance. So how do we estimate f, or function f, which we hope to describe a system with? There are two approaches. The first is these parametric methods, where we assume some functional form, for instance, b0 plus beta1 x1 plus beta2 x2 and so on, and we tune our coefficients beta by training our model to some training data. That is, we fit the coefficients to some training data to reduce the loss, making our model match as closely as possible to the data. An example of this is shown here for a two-dimensional space of descriptors, where the goal is to predict the income. So this is for basically predicting the income of a person, given it descriptors of education and seniority. The two-dimensional plot is shown over here, where we have a plane that describes our function, given intercept beta0 and coefficients beta1 that adjust the importance of education in the model, and beta2 that adjust the importance of the seniority in the model. The observations for the data are shown in these red dots, and again the model is this plane here. Okay, this is fairly easily interpretable. We have different parameters, beta1 and beta2, that corresponds to education and seniority, helping us to see how these descriptors map to the y value, or the output, in this case the income. Now, one key advantage of this approach is that the model you guess will describe the data may not describe it well, because underlying functional form is unknown in many cases. One way to combat this issue is to allow or to choose some very flexible model, but typically these flexible models require a greater number of parameters, are harder to fit, and are susceptible to something called overfitting, which we will talk a bit more about in a few slides. Non-parametric methods are those which don't make an explicit functional form for f, and those include things like decision trees, k nearest neighbors, and support vector machines. We'll talk about at least two of these before the end of the workshop. Important discussion is the trade-off between prediction accuracy and model interpretability. Often the relationship is not something that's ideal. The bigger the interpretability is the lower the flexibility, and the higher the lower the interpretability, the higher the flexibility, which is not an ideal relationship. For instance, we can take lasso, which is a model that is similar to least squares regression with constraints. That is the least flexible but the most interpretable, and something that is most flexible, like support vector machines, is the least interpretable. Now, the most restrictive approaches, for instance these parametric models, are nice for inference, but models that are more flexible aren't good for inference, because often the functional form f is difficult to interpret. Again, if you take a linear model, which is this restricted model, we can study the coefficients of x1 through x to p, understand the relationship between x or y and the x values. Another class of category of models which you can consider carefully is the class of supervised models versus unsupervised models, or supervised learning versus unsupervised learning. And supervised learning is perhaps what you're most familiar with. That's typically when you have labels associated with the data and you try to match your model to fit best to your labels. For instance, over here on the left, we have these circles and these x's, and they correspond to, say, ferritic versus anti-ferritic materials. And if we have some new material showed up over here that's unlabeled, you can make this decision boundary here and say anything to the left of the boundary is supposed to be an x, anything to the right, or rather right is supposed to be an x, anything to the left is supposed to be a circle. And this model depends on the labels to make a prediction, to train and then make a prediction. Now over here on the right is an example of unsupervised learning, where the goal is to look at the descriptor space x1 and x2, for instance, and learn that there are some patterns in the data. And the pattern here is that there are some clusters of points, and this can help you to investigate, for instance, a similarity between each point within a given cluster, and you might find that they share some common property, which gives you some insight into how the materials behave, or the data behave. Again, for supervised learning, each observation, x sub I, is associated with some response, y, and the aim is to fit the model to best match the response given a particular x sub I. And there are two goals: to make accurate predictions, and also to better understand the relationship between the response variables and the predictors. And this is an inference. And for unsupervised learning, the goal is to compare the observations and their features, to search for patterns within those features, or a vector of measurements, without having an associated response or output y. Two important categories which we mentioned before are those of regression and classification. In both cases, the variables can be either quantitative or qualitative. The quantitative variables can be numerical. For instance, they can be age, height, income, the price of a home, and so on. And qualitative variables typically take on one of k different categories which are predefined. For instance, one can be male, female, or non-binary. For product brands, you can define the brand to be A, B, or C, and so on. Typically, regression problems aim to predict some numerical value, and classification problems aim to predict one or more of k different categories. Now, to assess the model performance, there are a few things one can do. For the regression, one can use the mean squared error formula, which is shown here. This is the actual value for y. This is the machine learning estimate for y. And you square the sum, square the ith value, and you take the sum, and eventually take the mean. And you can do this for the training set, in addition to the validation set or the test set. An example of this is shown here, where we have some points which constitute our training data, and we can tune M and C to best match those data. We can calculate the mean squared error to see how good the fit is. Then we can take the test data the model hasn't seen, and then calculate the kind of mean squared error distance from the prediction to the points the model hasn't seen to get a sense of how good the model is. Now for classification, it has to take a slightly different scheme to estimate how good the model is, and the training error rate is described with this indicator function, which just is a 1 if the prediction is equal to the actual value, and it's 0 if it's not. And you take the sum and divide by a total number of candidates or rows or data points that you're looking at. An example of classification is this so-called k nearest neighbors. So how does it work? Essentially, you have some points that are labeled. So we have, in this case, these blue squares and red triangles. We have some new point here, this green circle, which we don't know how it's labeled. And the scheme here is to look within a square and take the majority class to assign label. So in this case, within this radius here, there are 2 triangles and 1 square. So the model says to assign this unknown point to be a triangle, because there are more triangles than squares. However, if we take the radius to be this value here, we count the number of labels within this circle. We have 3 squares versus 2 triangles, and we'll assign this unknown point to be a square as opposed to a triangle, because there are more squares. So you can tune this radius to get a different value, but this is the kind of the game you're playing in order to increase the accuracy of your model. This is an example of the classification using k nearest neighbors. On the left is the 15th nearest neighbor classifier, distinguishing between the orange circles and the blue circles, and the algorithm defines this decision boundary shown here, which seems to do a reasonable job of classifying the points. We compare that to a linear regression type approach, where we make some line to make a decision boundary between the points. You can kind of see that it doesn't do as good a job as the k nearest neighbors. Another classification algorithm is that based on decision trees. There is a decision tree model, and there's a random forest regression, which we'll talk a bit more about in a few slides, but we'll focus on the kind of basic form of that, which is the decision tree, for the next few moments. Consider these data. These are data for ferromagnetic transitional metal alloys, and the plot here is atomic volume on the horizontal axis and calculated chemical hardness on the vertical axis. And I'm labeling these plots with closed squares, which are non-magnetic alloys, and open squares, which are ferromagnetic alloys. If you zoom in on this region, there's an interesting pattern that emerges. For a given region of our two-dimensional descriptor space, we find only ferromagnetic transition metal alloys, and outside this region, they're only non-magnetic alloys. So with this pattern in the data, we can say if we have a new point Over here, which we don't know the label for, we can guess a label given the pattern of data. This, for instance, should be non-magnetic. If we find an unlabeled point shows up in this part of the descriptor space, we can guess that it should be ferromagnetic. Now this scheme lends itself to a decision tree very nicely. We could, for instance, say, given the chemical hardness, if it's greater than 0.25, guess that it's non-magnetic. If it's less than 0.25, look at another descriptor, atomic volume. If that atomic volume is greater than 40.6, predict it to be non-magnetic. If it's less than 40.6, predict it to be ferromagnetic. So that's essentially divvying out the descriptor space for these values here and these values here, defining the regions where they're ferromagnetic and non-magnetic. It's a very nice scheme and very simple model, and does remarkably well for this data set. Let's return to regression and use that to think about how to best choose descriptors, which again is an active area of research. Let's use a simple-minded idea to address how one might choose descriptors. In this data set, we have housing prices, where the price is plotted on the vertical axis, and a descriptor, the constructed area, is plotted on the horizontal axis. What one typically does is, or should do, is visualize the data first. So this is a scatter plot, data visualization. And looking at the visualization, you can see that there's some correlation between the constructed area of the house and its price. And with this in mind, one can perhaps guess that the constructed area should be a reasonable descriptor for predicting the housing price. One can iterate through a list of descriptors, inspecting them for the correlation or some other relationship that could hint at their use as a descriptor. Also, one can use domain knowledge to figure out whether or not the constructed area is a good indicator of the Y variable or price. For instance, you could talk to a real estate agent and ask them, would a constructed area be a good descriptor? And with their knowledge of the field of real estate, they would tell you yes, it is likely to be a good descriptor, and perhaps give you a list of other potentially good descriptors for predicting the price. And the idea is you can do something similar for materials research, inspect some descriptors visually, and also with some tools, for instance, calculating the Pearson correlation coefficient, and think critically about the physics of the data, and use that to construct a reasonable set of descriptors. Okay. Now, the goal of building a good model is to have the model be generalizable. That is, the prediction should be sound for data the model hasn't seen, not just the data a model has been trained on. Typically, we play tricks with the statistical modeling to ensure that the model is generalizable, and these tricks include resampling methods or validation. Now, let's talk about resampling methods. That's typically drawing samples randomly from the data set to refit the model over and over again, see how the model performance varies with choice of randomly sampled data, training data. This gives you an idea of how uncertain the model is, how much error the model is in predicting the data, and allows one to get a sense of how model performance is, and what the model performance is. Typically, one uses this validation scheme, validation set approach, to divide the data into a training set, a validation set, and a test set to best estimate the model performance, and also tune the model. We'll talk a little bit about that in a few slides. The training data is creating estimates for the coefficients. Relation set allows you to choose the model, and the test set is something that's used at the very end of the model creation, which allows you to explore how your model is performing. And typically, you don't tune your model using you never tune the model using your test set. An example of validation techniques include this leave one out cross-validation. There's also k-fold cross-validation, in addition to the bootstrap technique. And I think the k-fold cross-validation is perhaps the most widely used, at least by me, and so let's talk about that. So for that means we divide the training set into k-folds. In this case, there are 5, where 4/5 of the data are used for training, and 1/5 is used for validation, and you cycle through the 1/5 bins of data, where you then make this bit your validation set and these bits your training set, and calculate the performance and iterate such that you get 5 estimates for the performance, and you take the mean to estimate the overall performance. It's typically more reliable than just taking one training validation split, because you can suffer from something called overfitting. This tends to diminish the amount of overfitting you have, and we'll talk a little bit more about overfitting in a few slides. Now, typically you have a choice of models and choice of hyperparameters and choice of descriptors, and there are different things you can do to select the best one. Often selecting different descriptors, for instance, is important for optimizing your model. There are a few ways of doing that. The first one we'll talk about is subset selection, where you select carefully a subset of the potential or total number of candidates you have for predictors, also known as descriptors, to optimize your model performance. There's also a shrinkage or regularization, which will involve taking all your predictors or descriptors at once and applying some scheme to shrink the coefficients of some of the descriptors towards 0. And there's also the dimensionality reduction tools, which takes all your predictors, maps them onto an m-dimensional space where m is less than p, and then you can take this reduced space to train your model. That is, you take your mth projections and train your model using those reduced dimensional descriptor space of size m. And again, m is less than p. So this is important for overfitting. And overfitting is shown or demonstrated using these graphs here. In each graph, there are 3 of them. The data are the same, and the goal is to make the best model. But if you use too many descriptors, you can fit to the noise, which is what's happening over here on the right. Even though the model here is perfectly fitting to these data set, you can kind of tell by looking at it that it's not a good fit. This is a high variance or overfitting scenario. That's because you're having too much variability in your model. Now let's go to the left here, where we have a very simple model. Linear model used to fit these data, and you can kind of tell that it doesn't really capture the underlying behavior of the data, and it underfits is a term that one uses. Now, if you go in between that, if you started from say high variance case and reduce these theta 4 and theta 3 to close to 0, or just eliminated them entirely, you can get to the case that's just right, where the model is capturing underlying behavior of the data but not fitting to the uncertainty or noise in the data. And we use these sampling methods and subset selection, shrinkage, and dimension reduction methods to obtain this just right model and to avoid overfitting. An example of subset selection, we scan through a set of predictors of varying numbers and calculate the validation set error and choose the number of predictors that has the lowest error. For instance, in this case, 6 has the lowest error and 2 or 1 has the highest error. For the shrinkage methods, one uses the so-called ridge regression and lasso. Let's talk about ridge regression first. Ridge regression is none other than least squares fitting, or typical linear regression, plus a constraint. So this is a linear regression, which I label RSS here. It shows up again here. And to make the ridge regression different, we add plus lambda, the coefficients squared. So lambda is the regularization parameter, where when it's 0, we get none other than the linear regression back, but when it's non-zero, we get ridge regression. And it turns out this presence of this lambda here, or rather this term here, forces the coefficients in the model to be closer to 0 and regularizes them. If you look at this effect graphically, as lambda grows larger and larger, the beta coefficients grow smaller and smaller, limiting the impact of some of the coefficients, which may reduce overfitting, giving you a more reliable result. Now for lasso, the case is very similar to ridge regression, except that the form of the constraint is a bit different. Instead of beta squared, we just have absolute value of beta. And this actually has a very interesting impact on the performance of the lasso. So instead of having the coefficients go close to 0, you can actually have the coefficients go to 0. So again, we're increasing lambda here and looking at the coefficients. As lambda goes large, some of the coefficients go precisely to 0, not just close to 0, as was the case for the ridge regression. Of course, as lambda goes to infinity, then the coefficients will go to 0, which is not the case for lasso. They can go to 0 before we get lambda is infinity. So how does this work? Well, if we plot the beta 1 on the horizontal axis and the beta 2 on the vertical axis with the lasso on the left-hand side, regression and ridge regression on the right-hand side, we take these concentric circles to be the contours of the error given beta 1 and beta 2. We see that we can reduce the error by having some choice of beta 1 and beta 2 combination, and that, for instance, for the lowest error contour, because of the shape of this constraint here, the absolute value is opposed to the beta squared, we can get precisely some value, for instance, beta 1 to be 0 here, and it's small here but not actually 0. So this is why you can get 0 coefficients for lasso, but only close to 0 coefficients for ridge regression. Depending on what you want to do, you choose one over the other. Okay, now let's look at dimensionality reduction techniques to reduce the space of our descriptors. One popular tool for doing that is principal components regression, or principal components analysis, and then subsequent regression, or linear regression using the PCA components. PCA analysis involves dimensionality reduction by taking most variance in the data and finding an axis. We'll call that the first principal component. And the next one is going to be orthogonal to that and has the second most variance in the data, which happens to be along this direction. And we redefine the descriptors to be the first principal component and the second principal component. Now this isn't so impressive in 2 dimensions, it's more impactful in high dimensions. Let's take this 3-dimensional space. You can kind of tell this disk isn't very much along out of the plane. And so you can define one vector to be PC1, the next vector here to be PC2, and the third one here to be PC3. And what you can do is just take this component and that component, and those two components describe most of the behavior in the data. You could ignore the third shown here, thereby reducing your space from 3 to 2, but still capturing most of the behavior in your data. This is another example with population on the vertical axis, or horizontal axis rather, and ad spending on the vertical axis. You can find where there's most variation along the data and redefine that to be a first and second principal component analysis, or principal components as is shown here on the right hand side. Okay, now why do we want to reduce the dimensionality of space? That's because life can be a little bit difficult in high dimensions, even for a machine. And that reason for that is the following. Most statistical regression tools are built for the case where the number of observations is much bigger than the number of features. But recently, with modern technology, the ability to collect large numbers of data, and also a large number of features, this number P can get quite large, comparable, or bigger than the number of samples. And this is especially the case where the number of observations, N, can be limited due to sample availability. Now, datasets where there are more features than observations, features is another term for descriptors, are known as high-dimensional datasets. Now, typically, your tools for subset selection, regularization, regression, and lasso are good for tackling high-dimensional data because they reduce overfitting, as we discussed before, by using a less flexible model. A graphical representation of the issue with a high-dimensional space and why it's an issue is shown here on the left. We have a typical n is greater than p case, or in this case, there's just one descriptor, and there are very many observations. In this case, there's just one feature, and we just have 2 observations, and so our number of observations approach the number of features, and we have this perfect fit. But you can imagine you can make 2 points to fit a line, but you have no idea of whether this line is going to be really describing the data set well or not. And of course, if you increase the number of x values to x sub n, as long as n is less than the number, or x sub p, let's call it, number of features, as long as x sub p is larger than number of observations n, then we still have this issue, but in a high-dimensional space. Now let's look at tree-based methods to do not just classification, but also regression. some decision tree basics. So a decision tree is essentially this object that has these descriptors, which we talked about before. And this example is for a hitters data set, which is based on baseball. And there are two descriptors: years, number of hits, and you can assign some numerical value at each node in the tree. It looks something like this. Given the data set with years on the horizontal axis and hits, number of hits on the vertical axis, you can use your tree to assign some number to points in this region, and this region. So we're partitioning our data set using the tree. It also looks like this, where y here is our value for the numerical value when I assign to different regions. And we have two descriptors, x1 and x2, in this feature space or predictor space. Now, what you can do is you can apply this to create a random forest, that is a collection of decision trees can be used to create a random forest, collection of trees that can be used to do a prediction. There's both classical, or rather classification, or regression. It takes some inputs x, has some output y. We take our data set and divide it into a training set and a validation or test set, and we tune our values v1, v2, v3, shown here, to optimize our loss function. This is an actual number we want to predict to. This is our prediction. So how does this work? Let's take a dummy data set, which is a sine function. F of x is sine of x. And we'll add some noise, and we'll see if this decision tree approach can fit or data. And let's start with a very simple tree with depth just 1. So the left of the node we have some prediction, which is about 0.5, and when we have v1 greater than 3, to the right we project about minus 0.75. So this is our estimate for a function f of x given depth 1. Now, if we allow our tree to become more sophisticated, we allow depth 2. That is, allow not just depth 1, but depth 2. We have more sophisticated prediction. We have more variability in our prediction. And it starts to approach the behavior of the sine curve, but it's not so good still. So let's go a little bit deeper. In depth 3, we have a pretty good approximation to the sine curve. And if we go even further to depth 5, now we're starting to fit to the noise, which we really don't want to do for any machine learning model. We want to capture the underlying behavior of x, or the sine of x in this case, while avoiding fitting to the noise. So our random forest is a collection of decision trees, which is bootstrapped on training sample. So you sample the training set differently, you train different trees. The random forest is random because each tree is created for a different subset of descriptors or predictors, and each split is allowed for only one predictor at a time. Typically, the number of predictors you take is the square root of p. So the subset of predictors you take is square root of the total number of predictors p for each tree. And by taking a random sampling of a subset of the descriptors or predictors, you can make the tree less correlated. That typically gives you a better overall average result. Now, notice I said average result because each tree is averaged to get a good prediction for the entire forest. This is a particular example shown here on this graph is for classification. So you take a random set of decision trees, tree 1, tree 2, tree 3, and that each tree predicts something different. So it predicts class A, tree 1 predicts class A, tree 2 predicts class B, tree N predicts class B, and you take the majority class. In this case, it's class B is what the random forest will predict, since in this picture, class B is the majority. So that's how random forest works. It's a collection of decision trees. Alright, now one can implement quite easily these trees and linear regression tools and lasso and ridge regression using Python modules. These include scikit-learn, which I think is the most popular, also SciPy, and there's also Keras, TensorFlow, and PyTorch, though these are for neural network applications which we won't have time to talk about today, but are of growing importance in the materials informatics community. Now, an example of using scikit-learn to implement linear regression is shown here. We import the module using this command. We can create a dummy data set. We can then import our model by calling linear regression, and then fit it to the data using this .fit function. Then generate our score by using the score function, and also print a coefficient and an intercept using the .coef and .intercept functions, and predict, estimate y given different values for x using the .predict function. We can also implement lasso, ridge regression, and random forests using scikit-learn. That's extremely convenient, very powerful tools. Now let's turn our attention to how we can apply our sophisticated machine learning tools to study magnetic 2D materials. Now consider a set of 2D materials based on chromium, germanium, telluride, where the chromium atoms are these blue spheres, the A sites. The germanium atoms are these B sites here and here, and the tellurium atoms are the X sites, 3 above and 3 below the plane here. Now this shows just part of the crystal that extends in X and Y, but is confined along Z to just one layer of these atoms. Okay. Now from the top-down view, we have these A sites or chromium atoms forming this hexagonal lattice. The center of each hexagon is the germanium atom or the B site, with 3 tellurium atoms or X sites above and below the plane. Now chromium, germanium, telluride, as we discussed before, is a ferromagnet. Interestingly, if we substitute germanium for silicon, we go from a ferromagnet to an anti-ferromagnet. We change the chemical composition of our CGT to CST, and we get a change in the magnetic order, which is surprising because we swap one non-magnetic atom with another non-magnetic atom in the same column or the periodic table, but we get a drastic change in the magnetic properties. Now, we can exploit this idea of changing the structure, the chemical composition of the materials, to see how that affects its magnetic properties by making very many chemical substitutions at the A, B, and the X sites. If we look at the total number of combinations of this, we get about 10 to the 4 different structures. We can take about a subset of 200 of those using density functional theory, taking different magnetic configurations, a non-magnetic case, a ferromagnetic case, and then anti-ferromagnetic case, and extract the formation energy for each configuration, and then the magnetic order and magnetic moment by doing some data analysis. In particular, we take one of two of the A sites in the unit cell and change it from chromium to something else, as shown here. We can make them titanium, vanadium, chromium, manganese, and so on. The B sites, we take combinations of silicon, germanium, and phosphorus atoms. For instance, the B sites can be both silicon or silicon germanium, or germanium phosphorus. And the X sites are going to be all sulfur, selenium, or tellurium. And if we take a look at the periodic table, this is how our A site substitutions are made, or B sites, and or X sites. After calculating the DFT, we can collect the results and compare the ferromagnetic configurations with the anti-ferromagnetic configurations. Now, when the ferromagnetic configuration is less than the anti-ferromagnetic configuration, we would expect to find the lower energy configuration to be realized in nature. So when this delta E is negative, we should expect to find a ferromagnetic configuration in nature. When it's positive, we should expect to find an anti-ferromagnetic configuration. So here's the result with the A site substitutions on the horizontal, or rather vertical axis, the B site substitutions on the horizontal axis. Each panel now represents the X site substitution, so we have X equals tellurium in this panel, selenium here, and sulfur here. Now the color represents delta E, where the negative values are blue. These are the ferromagnetic configurations. And the positive values for delta E are the anti-ferromagnetic configurations. For instance, chromium 2, germanium 2, tellurium 6 is blue, which is ferromagnetic, as we expect from other calculations and from experiments, at least for bulk and bilayer. Now, there are purple squares here, which are indicating unconstrained anti-ferromagnetic configurations, which we don't have delta E for because the spin's flipped from FM to both AFM. And the black squares are the reverse, where the spin's flipped from AFM to FM, so we can't calculate delta E, but we know for sure that they're ferromagnetic configurations. So using this figure, we can estimate the magnetic order for each ABX3 structure. We can also calculate the magnetic moment for each ABX3 structure. The values are shown here for the vertical axis representing the A site substitutions. The horizontal axis represents the B site substitutions. Again, the panels are the X site substitutions for tellurium, selenium, and sulfur. The color now represents the magnetic moment. The darker the color, the larger the magnetic moment. We take chromium 2, germanium 2, tellurium 6. We know that if you substitute one chromium for one manganese, we get a little bit darker square, which means that we can increase the magnetic moment. You might notice that there's a pattern in these data that varies across the X sites and across the A sites and B sites. And the hope is that we can get a machine learning model to learn this pattern and exploit that pattern for quantitative predictions of the magnetic moment in this case. Now, the formation energy is also important because we don't only care about the magnetic moment, we also want to have some estimate of whether the material we predict in silico will be able to be made in the lab. And formation energy is a proxy for chemical stability, which is necessary but not sufficient for estimating the chemical stability. Now, the result for the formation energy is shown here. Again, the A site substitutions on the vertical axis, P site on the horizontal axis and the different X sites for different panels. Now the color here represents information energy, with a more negative value for information energy being more chemically stable. You notice that there's a pattern going from left to right in the first row of the position metals, and left to right in the second row of decreasing chemical stability, and increasing chemical stability going from tellurium to sulfur up row 6 of the periodic table. And again, we want to exploit patterns in these data with machine learning for quantitative predictions. Now, in order to build a model, we need to create some descriptors to describe our data. And for these, we use really simple-minded ad hoc descriptors that are collections of atomic properties, little p, where we estimate the property of a compound by taking the mean or the variance of these lists of atomic properties of the constituent elements. So for instance, if we do this, we get about 61 total descriptors, and for atomic properties little p, we use things like number of unpaired electrons, the atomic radius, the ionization energy of the atom, and so on. Using those descriptors, we use a model based on decision trees, this random forest regression. And we take as the inputs things like number of unpaired electrons or spin-up electrons. We want to predict now the magnetic moment. We divide our data set into training and test, and tune our coefficients of our model to minimize our loss. And if we do that, we can create a model to make these predictions of magnetic moment. And we can plot the DFT magnetic moment on the horizontal axis and compare that with the ML prediction of magnetic moment on the vertical axis, where this dashed line is the perfect prediction line, which is just a guide to the eye, and plotting my training data, my green circles against my test data, my red squares, and I find in both cases the points are falling pretty close to this perfect prediction line, indicating that our model is performing pretty well and generalizing fairly well, which is what we want. So we can use this model to not just make predictions, but try to learn some physics by analyzing the descriptor importances. In this case, the mean number of unpaired electrons is the most important descriptor for predicting magnetic moment. As you know by now, that's not surprising. And essentially, there's nothing surprising happening in this case. But if there was, we can ask ourselves, why is this descriptor important? And it's not expected to be, and potentially learn some physics. Okay. Now, we not only care about predicting the magnetic moment, we also care about the chemical stability. So we can use information energy and ML to predict values for potentially chemically stable compounds. So we can do this for random forests with DFT information energy on the horizontal axis and DFT or predictions of DFT information energy on the vertical axis. Again, the guide to the eye is this dashed line. All the points are falling fairly close to the line, so the machine learning model is performing fairly well. We can repeat this for kernel ridge regression over here on the left, and neural networks over here on the right. I won't have time to talk about these models, but you can get increased performance from kernel ridge regression and neural networks. Now, it took about half a year to create about 200 or so DFT calculations for these materials. And notice that I told you we had about 10 to the 4 potential candidates. We use machine learning to estimate in milliseconds on a laptop, once we train a model, thousands of different structures, the properties of thousands of different structures, and I'll show a subset of those predictions here for magnetic moment and information energy. And we can use our DFT and ML predictions to do material screening, going from a very large set of candidates to ones that are stable, and then ones that are stable then potentially large magnetic moment, by using certain screening criteria say greater than 5 megatons for the magnetic moment, and less than information energy for CGT. We get some candidates. I'm showing a few here. These were in our original DFT dataset. These were predicted by machine learning and then verified again, or later, by DFT. They are matching with the DFT predictions. So this is good, and we can essentially do a very large screening task very quickly using a combination of ML and DFT, much faster than we would be able to using DFT alone. Okay, now some resources to continue your self-study for materials informatics. Machine learning, you can get the book Introduction to Statistical Learning by Trevor Hasty and others. It's a very good book. It's available online for free via PDF. There's also Andrew Ng's Machine Learning Coursera course. One should know about Google Colaboratory, which we'll actually talk a little bit about today, in addition to Jupyter Notebooks and Scikit-learn, and perhaps Keras, TensorFlow, and PyTorch, if you want to get more familiar with neural networks and deep learning. For materials informatics, you can look at the main study I described today in this paper in Scientific Reports. Use this QR code to access this link very easily. Also, my group website, materials-intelligence.com, for a page where there are many resources, more resources than are shown here for machine learning and materials informatics. Now, an exercise for today, I'll describe it briefly before we jump into it. We will be using ML to predict information energies of ABX crystal structures. We'll run our Python code using Google Colaboratory. We will create descriptors, X values, information energies, Y values, and use those X and Y values to train machine learning models after breaking it up into training and validation and test sets. We'll only do linear regression and random forest regression today. You can try playing with other models later. And we'll also do a little exercise on hyperparameter tuning, which is very important for machine learning, optimizing your machine learning models. The data is available here. You can read a little more about how the data were created in the paper, which link is shown here. Now we'll download the data and we'll create some plots first, then use linear regression to create some models to predict the results in the data, and then use random forest to do the same afterwards. This is a table of the most important descriptors that I found. We'll be playing with the top 6 today, and feel free to choose one or more than one of these descriptors to build your models. Now, to get started with Google Colab, you need to have a Google account and install Google Colab on your Google Drive. This is a link to the Google Colab page. And to access the particular Google Colab notebook for this exercise, please go to this link, which I will share in the chat. And to get set up with the Google Colab notebook, you click on the link to download the notebook that I have, import it to your Google Drive, in addition to the CSV file, if possible, straight from the Google Drive or from the website. Then copy the files to your Google Drive, install Google Colab if needed, and once you've done that, open the Jupyter Notebook using Google Colab to get to a page looking something like this one. And then, once you've done that, run the cells in the notebook, adding code as needed, and we'll walk through the exercise next.